So we're going to try a different technique this time called T-charting, where the topic is placed on the left-hand side of the table and the definition on the right-hand side. This enables the reader to identify keywords and their meaning and make clear notes. The first definition is thermochemistry, which is the study of energy changes that occur in a reaction. These energy changes can be classed as exothermic, where a reaction gives off heat, or endothermic, where a reaction absorbs heat. Both endothermic and exothermic reactions are measured in kilojoules per mole. The heat of reaction is defined as the energy that is absorbed or liberated in the chemical reaction. A calorimeter is a device, such as a polystyrene cup or a glass beaker with a thermometer, that measures the heat of a reaction. The thermometer enables the measurement of small temperature changes due to these reactions. Enthalpy is defined as the heat content of a substance, which includes its internal energy and is related to vibrations, rotations, and translational movements within and between molecules of a substance. However, in practice, it's difficult to measure this enthalpy, and so it is measured as a change in enthalpy and defined as delta H. Delta H is the heat absorbed or released per mole of reactant as the reaction is written at constant pressure. The enthalpy of the reaction is simply the enthalpy of the products minus the enthalpy of the reactants. This gives a way of looking at endothermic and exothermic reactions. Enthalpy is always negative for exothermic reactions and positive for endothermic. This seems confusing until you look at an enthalpy state diagram. In an enthalpy state diagram, the enthalpy is on the y-axis and the time or the extent of reaction is on the x-axis. This shows the state of the reaction. The reactants are at this initial position here and the products are in the final position here. This is the relative enthalpies. A change in enthalpy of this reaction is the products minus the reactants, which is positive, hence an endothermic reaction. If the reactants have a higher enthalpy than the products, then the change in enthalpy, the product minus the reaction, is negative, and this is classed as an exothermic reaction. So what happens to the heat? Where does it come from? We define two things in the system and the surroundings. The surroundings is the environment around the system. In an endothermic reaction, heat is supplied from the surroundings to the system to enable the reaction to occur, and it causes a decrease in temperature in the surroundings. In an exothermic reaction, the heat is released from the reaction and is given to the surroundings, causing an increase in temperature. There are several rules for using heats of reaction, although I prefer the term enthalpy of reaction, as it's more correct. If the reaction direction is reversed, then the sign of the enthalpy is also reversed. This means an endothermic reaction becomes an exothermic reaction when it progresses in the opposite direction. Since the enthalpy is defined as the energy per unit mole of the reactant, if the number of the moles of the reactant changes in the reaction as it's written, the enthalpy will also change. It will be multiplied by the number of moles of the reactant. It is also important to include states, such as solid, liquid, gas, and aqueous states, as the enthalpy of a reaction often depends on the state of the reactants. A specific example of an exothermic reaction is a combustion reaction, where the reactant is reacted with oxygen to form carbon dioxide and water. Sometimes nitrogen dioxide or sulfur dioxide are produced instead, but in most cases it's carbon dioxide and water. Because it's an exothermic reaction, the enthalpy of a combustion reaction is always negative. It liberates heat. An example of a combustion reaction is methane, which is reacted with oxygen. The first step is to balance the equation. We need 2 waters and therefore 2 oxygens. The delta H from the table in chapter 14 is 890 kilojoules per mole of methane. That should be negative 890 kilojoules per mole of methane, as it's an exothermic reaction. To solve an enthalpy of reaction problem, you need to define your variables. You'll generally have a change in temperature, a certain mass of water or solution, and the heat capacity of water or the solution. You also have a mass or number of moles of reactant, which causes the heat to change. Using the formula in delta Q is equal to mc delta T, you'll get a change in heat energy for the water or solution. If you include the the number of moles of reactant, and enthalpy for the reaction. To find the number of moles, we sometimes have to use N is equal to M over M. So mass over molecular mole, mass. Several assumptions are made in these calculations. We assume that there's no change in the temperature of the vessel, either the polystyrene or the glass vessel. We also assume that the solution has the same heat capacity of water, which is often the case. It also assumes that it has the same density. This is particularly important when using volumes instead of masses. It also assumes that there's no change in volume or density of the water when some solid is added or when solution is added, so during the reaction process. An example of such a reaction is solid sodium hydroxide dissolved in water. This probably changes the volume very little and the density even less. But if there's two solutions, such as sodium hydroxide plus water, then you'll need to modify the mass to include the total mass of both solutions. For a combustion reaction, a similar example can be used, where a source of fuel heats up a calorimeter which has a temperature change. We need delta T, the mass of water, the mass of the glass vessel, the heat capacity of the water, the heat capacity of the glass vessel, and the mass of the reactant that is used up. The heat of reaction can be calculated by using delta Q for water and the glass. The number of moles of the reactant is actually the change in the mass between a full container and an empty container. Again, this makes several assumptions. It assumes there's no heat loss to the environment. It assumes that all the heat generated goes into the water. And it assumes that the glass and the water are both at the same temperature. So as you can see, T-charting can give a structure to a set of notes. It's a useful way of summarizing what is important in a chapter.